Hello everybody, welcome into another lesson. So today we are going to talk about the area of regular polygons. Now for today's lesson we are going to focus strictly on regular pentagons and regular hexagons. But what I'm teaching can also be applied to triangles, squares, rectangles, octagons, decagons, you name it. But I figure we've already dealt with our quadrilaterals and triangles to death. I'm not going to bring those up again. But I am, however, going to talk about hexagons and pentagons with these. So we have here a regular hexagon. Now, the idea is, and I've said this in the circles unit when we were talking about this, every shape has a circle circumscribed about it, though we just can't see it. So, like you would in a circle, you have the center of the regular polygon. In this case, the regular hexagon. So, here you have the center of the hexagon. And just like you would in a circle, you have a radius of the hexagon. The radius of a polygon in general goes from the center to a vertex of that polygon. And then you have here what's called, when you draw a perpendicular line from the vertex, well, before I talk about that, when you have two radii formed that intersect, that form this angle here in the polygon, that is the central angle. These two radii form a central angle, just like it would in a circle. Now, if you take a line, draw an altitude that from the vertex of the central angle to the base, that's called the apothem. That is the apothem there. Now, so we've covered all that. So to find the area of a regular polygon in general, it's going to be half the length of the apothem times the perimeter of the polygon. And of course you got the base, you take the length of your base, multiply it by however many sides the polygon has, you got your perimeter. So that's how you would solve that. And in general, then, that central angle is going to be bisected into two right triangles. And of course, your central angle itself would be bisected. So sometimes it's going to require a bit of trigonometry to solve, or your 30, 60, 90 triangles to solve. Oftentimes, all you're going to be given is the length of your radius. You'll have to use either trigonometry or 30, 60, 90 or 45, 45, 90 right triangles to solve for the length of your base and your apothem. So we'll get into some examples here. Let me move that a little bit closer so it's easier to see. There we go. Sorry about that, folks. So let's go ahead and do some examples here with a let's do some examples here with a hexagon, I think. Hexagons would actually be easier to start with than pentagons. There's a reason for that. Alright. So, let's see. Of course, we got the center of this hexagon. There's your center. Let's get into some exercises here. Alright, so first thing we have here, let's draw the radius. They give you that the radius of this hexagon is 4. We have a radius of 4 in this hexagon, so that's something we do know. Alright, I'm going to draw the apothem here, and what do you know? We form a right triangle. We don't know the base, we don't know the apothem, and of course we don't know the perimeter. We have to solve for all those things, and then we can find the area. So this is often what problems will look like when you're solving for the area of a regular polygon, in this case a hexagon. The first thing you need to do is ascertain your central angle. How do you find the central angle of a regular polygon? The central angle can be found here. The central angle of a regular polygon is going to be based on the circumscribed circle around it, which is 360 degrees divided by the number of sides of the polygon. That's the formula for finding the central angle of a regular polygon. You take 360 degrees, which is the measure of the circumscribed circle, you divide that by the number of sides of the polygon. So in this particular case, it's a six-sided figure. So it would be 360 degrees divided by 6 sides, which means your central angle is 60 degrees. Alright, so we found the central angle to be 60 degrees. That's great. But if we drew the apothem from the central angle, that bisects that central angle. So what you really have here is a 30-degree angle then. If you've bisected the central angle, it's 30 degrees for this angle here. You now have a 30, 60, 90 right triangle. We're going to call this length of the base here half of b, because this altitude, the apothem, also bisects this base. So what you're really getting is only half the length of the base, right? Now we can go ahead and solve for these lengths. So we have, again, a 30, 60, 90 right triangle. What do we know about 30, 60, 90 right triangles? That the shortest leg across from the 30-degree angle is going to be half the length of the hypotenuse. So that means that shortest leg, half the base, is equal to half the hypotenuse. So that'd be 4 divided by 2. That means half the base is equal to 2, which we can actually go ahead and solve for the whole base now. That would be equal to 4. So the length of your base is 4. And let's go ahead and just fill this out for all these sides now. Now that we found the length of the base, we can go ahead and do that. We know the length of every base, so we can easily find our perimeter. Now, what's the length of the apothem? Well, to find the apothem, we know that's going to be across from the 60-degree angle. If the length of half the base here was 2, right? The length of the apothem would be across from the 60-degree angle. That would be the length of your shorter leg times the square root of 3. So the length of the apothem is going to be 2 times the square root of 3. Alright, so now we found the apothem to be 2 times the square root of 3. We've got all the critical information now that we need to go ahead and solve for the area. So the apothem is 2 times the square root of 3. A length of a side of the hexagon here is 4. So let's find the perimeter. The perimeter, of course, is equal to what the length of a side is, would be 4 times 6 sides. The perimeter equals 24. So we found the perimeter to be 24. Now all we have to do to find the area is take half the length of the apothem, which was 2 times the square root of 3, times the perimeter, which was 24. So let's see, it's 24 times the square root of 3 for the area. If you wanted it exact, you would leave it like that. But we're going to do a decimal approximation to one decimal place. So the area is exactly 24 times the square root of 3. So let's do a decimal approximation. That'd be about 41.6 square units. So the area of this regular hexagon is approximately 41.6 square units. And I do got more examples here. Alright, I think we grasp the central angle now. That's pretty easy. I'll do 3 more examples with a hexagon, then I'll do 4 examples with a pentagon, and that'll be it. Won't be a super long lesson today. There's no need for that. Alright, this time they give us that the apothem is 5 times the square root of 3. So we know the length of the apothem. Sometimes you'll only know one length. You still need to find the length of your radius, the length of, to start with, half a base, then your perimeter and your area. So we got that the apothem is 5 times the square root of 3. I'll write that over here. Well, this is a 30, 60, 90 right triangle, right? Because this is a regular hexagon, your central angle is 60, so half of that's 30. Well, the apothem is across from the 60-degree angle. To find the length of half the base here, which would be the shorter leg of this right triangle, that's across from the 30-degree angle, you would just take the length of the apothem and divide it by the square root of 3. So you can say half the base, which is the shorter leg, is equal to 5 times the square root of 3 divided by the square root of 3, which means half the base is now equal to 5. That's going to come in handy. Keep that half a base. Half a base is equal to 5. Then if you want to get the length of the whole base, just multiply both sides by 2. You would end up getting 10. So the length of the whole base, we could put this anywhere since it's a regular hexagon. The length of the whole base is 10. We got the length of half the base. Now we can easily go from here and find the radius, couldn't we? The radius in a 30, 60, 90 right triangle is what? That radius, of course, is going to be the length of the shorter leg, which would be 5 times 2. So that'd be equal to 5 times 2. The length of your radius would be 10. So we actually just solved for the radius. The radius has a length of 10. So there's one thing we needed to solve for. We got the length of a base being 10. We got the length of the apothem being 5 times the square root of 3. Now, all we need to do are find the perimeter and the area. So, the perimeter, you would just take the length of one of the bases, 10, times the number of sides. That would be equal to 10 times 6 sides. So your perimeter, of course, is equal to 60. So we found the perimeter of this hexagon to be 60. Now we can just solve for the area. The area, of course, is equal to half of the length of the apothem, which would be 5 times the square root of 3, times the perimeter, which was 60. which means the area is exactly 150 times the square root of 3 if we were to do an exact, but we're going to do a decimal approximation, of course, to 1 decimal place. 150 times the square root of 3 is about 259.8 square units. So this area of this regular hexagon is exactly 150 times the square root of 3 square units, or approximately 259.8 square units. I got 2 more for hexagons, then we will move on to pentagons. The pentagons are going to require a bit of trigonometry, so that's a little bit different yet. Okay, what do we got here for this particular one? We got that the length of the apothem here is 6. We don't know the other lengths, but that's okay. We can certainly get that. So I would definitely recommend, of course, since we have a 30, 60, 90 right triangle, since we know the length of the apothem, that's easy. That's equal to 6. What we should do now is find the length of the shorter leg, which would be half the length of the base. Well, the length of the shorter leg is the length of the longer leg, of course, divided by the square root of 3. So half the base is equal to 6 divided by the square root of 3, which means we can actually rationalize the denominator. So then you would get half the base is equal to 6 times the square root of 3 divided by 3. So half the base is equal to 2 times the square root of 3. Keep that in your memory there. Half the base is equal to 2 times the square root of 3. I'm going to put that here. Half the base is 2 times the square root of 3. So that means the base itself would be equal to 4 times the square root of 3. So we found the length of the base of this regular hexagon. I'm going to write that up here. Since it's a regular hexagon, all sides will be 4 times the square root of 3. So we've ascertained that now. Okay, well, we need to find the radius. In a 30, 60, 90 right triangle, the radius is twice the length of the shorter leg. So the radius would be equal to 2 times the square root of 3, which means the radius is equal to 4 times the square root of 3. So we have now found the radius to be 4 times the square root of 3. So let's see. We know the apothem, we know the radius, we know the length of a base. We can now proceed to find the perimeter and the area. The perimeter itself is going to be equal to the length of one of your bases, which would be 4 times the square root of 3 times 6 sides, which means the perimeter is exactly equal to 24 times the square root of 3. But we'll do a decimal approximation for the perimeter also. So 24 times the square root of 3 is approximately 41.6 units. So the perimeter is exactly 24 times the square root of 3, or approximately 41.6 units. Now we can find the area. The area is equal to half the length of the apothem, which would be 6, times your perimeter. We're going to put in the exact value for this, which would be 24 times the square root of 3, which, see that half of 6 is 3, times 24 is 72. So the area is exactly 72 times the square root of 3, or we'll do a decimal approximation to 1 decimal place. Which would be about 124.7 square units. So the area is exactly 72 times the square root of 3 square units, or approximately 124.7 square units. And I got one more here for hexagons, then we'll move on to pentagons. And this method is saving you from splitting this up into separate regions and using a whole bunch of separate shapes and crap like that you really don't want to have to get into and find a bunch of different areas and then add them together. I mean, that's a way you can certainly do it if you so desire, but why? If there's a shortcut, let's do it, which this is it. Alright, so what do we know with this one here? We got that the perimeter equals 12 times the square root of 3. We know nothing else. Well, the perimeter of this regular hexagon is 12 times the square root of 3. Of course, it's a 6-sided figure, right? To find the length of a base, you're just going to take that perimeter, which is 12 times the square root of 3, divide it by the number of sides this polygon has, which in this case is 6, you would get that the length of a base is 2 times the square root of 3. So that's easy. Length of the base is 2 times the square root of 3. Alright, so that wasn't so bad. Now, we want to find the length of half the base here for this right triangle. Well, half the base is just half of that value. That's going to equal the square root of 3. So, for this right triangle here, this 30, 60, 90 right triangle, the length of half the base here, which would be the shorter leg of it, would be square root of 3. Now from there we can find the apothem and the radius. The apothem, of course, is across from the 60-degree angle. That's going to equal the length of your shorter leg, which would be the square root of 3 times the square root of 3, which means the apothem itself is just equal to 3. So there, we found the length of the apothem. Now we just need to find the length of the radius. The radius, of course, is twice the length of the shorter leg, so the radius would equal 2 times the square root of 3. So we found the radius, which was missing information. Now we're good to go to find the area. We already got the apothem, we got the perimeter. Now we can find the area. And see, it's a little more work than what we've done so far, but these regular polygons really aren't that bad. Now, if we were trying to find irregular polygons, you'd probably have to split it into separate regions and figure out separate areas. But the area, of course, is equal to half the length of the apothem, which would be 3, times the length of the perimeter, which would be 12 times the square root of 3, which the area would be exactly 18 times the square root of 3. And then, of course, we'll do a decimal approximation. It'd be about 31.2 square units. So the area is exactly 18 times the square root of 3 square units, or approximately 31.2 square units. So that's it for hexagons. Let's do 4 examples here with pentagons. We'll see how different it is. Alright. Draw a nice big pentagon here. So here we have a regular pentagon, this time a 5-sided figure. So once again, I'll form the center, okay? Let's form the center. Let's even draw the different parts. So we'll draw a radius. I'll even draw the apothem for good measure. So let's draw the apothem of it. There we go. We've set up our right triangle, but it's going to be a bit different this time. We still have half the length of the base for this right triangle. Now, before I give out any lengths or throw out any lengths, we need to find the central angle. What is a central angle of a regular pentagon? So, the central angle in this case, of course, would end up being still 360 degrees for that circumscribed circle, divided by the number of sides of this regular pentagon, which of course is 5, which would end up giving you a central angle of actually 72 degrees. So, the central angle of a regular pentagon is 72 degrees, but when you draw the apothem here, that bisects the angle and, of course, the base. So really, you're going to have a right triangle with a 36-degree angle here, right? Since you've bisected the central angle. This is where trigonometry comes into play. And it's not the most fun. So, let's see what we've been given here this time. Again, we'll start out with a radius of 4. Let's see how that changes. So we need to solve for, of course, the base, the apothem, the perimeter, and then ultimately the area. We got the radius to be 4. That's easy enough, right? Now, it doesn't matter where you start, since we don't have a 30, 60, 90 right triangle or a 45, 45, 90 triangle or even regular Pythagorean theorem, because we only know the length of one of the sides, which is the radius, the hypotenuse. So we're going to start with the base. In this case, it would be half the base, right? So we're seeking to find the side opposite the 36-degree angle, and we know the length of the hypotenuse. Opposite and hypotenuse, that's the sine ratio. So set up your sine ratio. That would be the sine of 36 degrees is going to equal the opposite side, which would be half the base, over the length of your hypotenuse, which then, of course, half the base would be equal to 4 times the sine of 36 degrees, which means the length of your actual base is going to be 8 times the sine of 36 degrees. Now, in this case, since we don't have your normal shortcut right triangles, we don't even care about the length of half the base. We just care about the length of the whole base. So let's find a 1 decimal place approximation for the length of the base, okay? And again, a caveat here, make sure your calculator is set to degree mode. If it's in radians, you're going to get a wrong answer, which will screw up the rest of everything else. So 8 times the sine of 36 is approximately 4.7. So the length of one of the bases is approximately 4.7 units. So there you go, 4.7 units for the length of one of the bases. Now we just need to find the length of the apothem, which would be A. Well, in this case, the apothem is the adjacent leg to the 36-degree angle, and we know the hypotenuse. So, adjacent and hypotenuse, that actually relates to cosine. So, set up your cosine of 36-degree ratio. That's going to be equal to your adjacent leg, the apothem, over your radius, which would be 4. So the apothem is equal to 4 times the cosine of 36 degrees, which then will also do a 1 decimal place approximation for the apothem. So let's go ahead and do that here. 4 times the cosine of 36, that's about 3.2. So the apothem is approximately equal to 3.2 units. Now all that's left to do is find the perimeter and the area. The perimeter, of course, is going to be equal to the length of one of your bases, which would be 4.7, times the number of sides, which would be 5, which therefore means the perimeter is going to be equal, I should say approximately equal, because we were approximating with trigonometry. Everything here is going to be an approximation, unfortunately, because trigonometric values for the most part are non-terminating, non-repeating numbers, so we almost always have to use approximations for them. 4.7 times 5 is 23.5, approximately. So the perimeter of this regular pentagon is approximately 23.5 units. Now to find the area, of course, you'll take half the length of the apothem, which would be 3.2, times your perimeter, which is 23.5, and then we can get a 1 decimal place approximation for your area. So let's see here. Times 3.2 times 23.5 comes to about 37.6 square units. So the answer to this here for the area is approximately 37.6 square units for this regular pentagon. And I got 3 more, then we'll be done for the day. Alright, what do we got next? Of course, these angles are going to stay the same since we're still dealing with a regular pentagon, so that makes life easier. Now, we got the length of the apothem being 5 times the square root of 3. So this time we know the length of the apothem here being 5 times the square root of 3. We just don't know anything else. We need to find the radius, and then we need to find ultimately the length of a base and the length of the perimeter and the area. So in this case, if we want to start out finding a base, we need to actually do half the base in this right triangle. If you have this angle of a right triangle, you're relating the opposite side and the adjacent side. That's actually the tangent ratio. So you'll set up your tangent of 36 degrees is equal to the opposite side of half the base over the adjacent leg, which would be 5 times the square root of 3. And then, of course, half the base would be equal to 5 times the square root of 3 times the tangent of 36 degrees, which then means the base is exactly equal to 10 times the square root of 3 times the tangent of 36 degrees. So yeah, sometimes these can get pretty hideous. So that means the base itself will get a decimal approximation here to 1 decimal place. So let's do that. Alright, then we'll take that times the tangent of 36 degrees. That'd be approximately 12.6. So the base is about 12.6 units. So now we know the length of the base. Now we need to find the radius. The radius, okay, what we're trying to solve for is the length of the radius. And then we have the adjacent leg here, which is exactly 5 times the square root of 3. If you're relating adjacent and hypotenuse, that's going to be the cosine ratio. So set up your cosine ratio for 36 to solve for the radius. That's going to be equal to the adjacent leg of 5 times the square root of 3 over the radius. So then you have radius times the cosine of 36 degrees is equal to 5 times the square root of 3, which means the radius is exactly equal to 5 times the square root of 3 divided by the cosine of 36 degrees. Which then we can get an approximation for the radius to 1 decimal place. So let's go ahead and do just that here. 5 times the square root of 3, take that divided by the cosine of 36 degrees, you get about 10.7. So the radius is about 10.7. Okay, well, we now know the length. We know all the lengths we need to know. We just need to find the perimeter and ultimately the area. We have the length of a base being 12.6. So to find the perimeter, you just take the length of one of those bases, which would be 12.6. This will actually be approximate since we've done approximations. This will be times the number of sides, 5. So now we'll get a decimal approximation for 12.6 times 5. So let's see, 12.6 times 5 is approximately 63 units. So we found the perimeter of this regular pentagon to be 63 units. Now we can solve for the area. The area, of course, is equal to half of the length of the apothem, which would be 5 times the square root of 3, I should say approximately since we had decimal approximations, times your perimeter of 63. And then ultimately we'll approximate the area to 1 decimal place. So 1/2 dang it. You get about 272.8 square units. So the area of this regular pentagon is going to be approximately 272.8 square units. I think we'll just do one more. Actually, no, I think we get it here. I think we get what to do with regular polygons. So that's it for this lesson. Next lesson, we're going to talk about circumference and area of circles. So I hope everybody has a great day. Take care.